Okay, so once upon a time we had this Pi Vi over Ni, Ti equals Pf Vf over Nf Tf. And where this came from was this idea that there's relationships between all of these variables. And I'm going to formalize these and show you a quick little demonstration on the computer that hopefully makes these and make these make sense. So the first one that I want to make sure that you guys do at least know sort of by names is what we refer to as Boyle's law. And Boyle's law is the relationship between pressure and volume, right? And this is always the easiest one to start with. If we think about putting pressure on the y-axis and volume on the x-axis, and I'm going to ask you guys a couple questions as I go through here. Um, let's assume that I have a container, and do you see a picture of me sort of wiggling my hands in the top corner of the screen?
Yeah.
Okay. So let's imagine that if I take and I squeeze a container down, all right, I make the container really small. What do you think happens to the pressure in that container?
It gets higher.
Yeah. So when the volume is really small, the pressure is really high. And sort of the flip side of that is when the volume is really big, the pressure is really small. So we get this nice sort of curvy shape to it. And that's just the hallmark of this relationship. As the pressure goes up, that's because the volume went down. You've literally got less banging of the gas molecules against the walls of the container. And so as the pressure goes up, the volume goes down. And we could also sort of say as pressure goes down, it's going to be because the volume went up. So there's this sort of inversely relationship. And Boyle's law doesn't care anything about number of moles or temperature. So what we can do is we can just say that, hey, if we just focused on the P and the V, that would give us what Sir Robert Boyle kind of figured out. And so let me just show you this on a little simulation real quick. I think I can just change over here. Let's see. Maya, since I know your microphone's working there, if you don't mind giving me are you seeing now like gas molecule simulation flying around?
Yeah.
Okay. All right. So all I'm going to do here is I'm going to change the volume. So right now we're at roughly 20 atmospheres of pressure, and and we're also at 10 units of width. So I'm going to basically cut the volume in half. All right. And this is, so just to make a prediction here, Maya, I've just cut the volume in half. What do you think that does to the pressure that we're going to see in just a second? Bigger or
Um,
smaller?
mm, Smaller, or I
Okay.
don't know.
That's okay. It's okay not to know. So we've made it smaller. Are the particles going to be more crowded or less crowded in there, Maya?
Um, More crowded.
Going to be more crowded. And so when they collide against the walls of the container, there's more collisions. And I think I said that the pressure was 20. Hopefully you guys see now that the pressure is 40. So we've got this relationship where the one thing went down by a half, it was divided by two, the other thing went up by two. So there's this sort of nice up and down relationship going on. So if I go back out to 10, let's see if we can make a prediction going the other way. All right, so right now, if I'm at 10, I don't know if I can go out to 20. Let's see if it'll take me all the way out there. No, it'll only go to 15. Let me go over there to Jack. Jack, now that the volume is bigger, what should the pressure do?
Go up.
All right. Are the particles going to be more crowded or less crowded?
More crowded.
So they were here, right?
Oh, less crowded.
They're going to be less crowded. So do you think that they're going to be colliding with the walls of the container more frequently or less frequently?
Less.
Yeah. So actually, what's going to happen to the pressure here, Jack?
Oh, it'll go down.
It will go down. And so we see this relationship, right? Right now it's at 13.2. Now it's at 13.9. So as I squeeze those particles a little bit closer together, the volume is going down, but the pressure is definitely going up. All right. So let me jump back over here to where I was with my piece of paper. And the important thing to realize is this relationship was first discovered by Robert Boyle, which is why we gave it his little name there. And it comes down to the fact that P times V is always going to just be some sort of a constant. All right. So if I have some sort of pressure and some sort of volume, and I come along and let's say that now the volume is 1/3 as large, right? How do I undo dividing by 3? Well, the pressure would have to be multiplied by 3 because those 3's have to cancel out. That's the only way I can get back to PV equals PV. So there's this sort of ratio type of thinking that you have to do, right? So that was the first one. I'm going to pause for a second. Do any of you guys have a question before I look at another one? It's okay to have questions, guys. It's also okay not to. Okay. So let's look at the second relationship. So that first one was just between pressure and volume. The next one, and these are all named after the people who first kind of collected the data and analyzed it and came up with these mathematical relationships. So the second one we're going to look at is Charles' law, right? And again, all of these, it's not like you really have to remember that PV equals PV, because if you go back and look at this, if we just covered up the bottom part of that equation, we'd have PV equals PV, right? So that's Boyle's law sitting right there. Charles was a guy who looked at the relationship between volume and temperature. And so let's kind of go over there. I'm going to stick with you, Jack. Let's think about warming up a gas. The gas molecules, as they warm up, Jack, are they going to be moving around faster or slower?
Faster.
Okay, and so they're going to hit the walls of the container. And are they going to be, if they're moving faster, do you think that they want to make the container bigger or make the container smaller if it's like a balloon and it's stretchy and able to change
Bigger.
shape? Yeah, it's going to make it bigger. So as the temperature goes up, what should the volume do?
Go up.
Yep. And so it does this nice sort of straight line relationship. And Riley, welcome. Can you hear me and see me there, Riley?
Yeah, I can.
Okay, good enough. You can go ahead, if you don't want to do a video camera, you can go ahead and just kind of turn the video off, but definitely mute is perfect. So this one, Charles' law, welcome Riley, it's nice to see you, is a relationship between volume and temperature, all right? And I may have to go grab another pen if this pen runs out. So volume and temperature. And so the relationship is as the temperature goes up, the volume goes up. And as the temperature goes down, the volume goes down. All right. And so if we go back and we look at our old friend, the combined gas law, if I were to ignore all the other pieces, and I'm going to come back to you here, Jack, all right? If P and N were ignored, I'd be left with V over T equals V over T. So V over T has to be a constant, okay? So hopefully this kind of makes sense, and I want to show this to you guys on the simulation. So if I go back over to here, so what we're looking for here is if I change up, oops, sorry, forgot to click the share button. Jack, can you tell me, are you looking at the gases again, the molecules bouncing around?
Yeah.
Okay, cool. All right, so what I'm going to do is I'm going to look at the pressure right here. Pressure is 24.5. I've got a volume right here, and I think I can do this just by, let's see if this does it. Oop, that's not exactly what I wanted to show you, so let me change that up. All right, so we inject some molecules in here, bloop, bloop. And what I'm looking for is some sort of relationship between the volume and the temperature. And so what I want to do is, let's try that. Let's try that. So I'm going to go ahead and, darn it, I had this all figured out. No, that's not doing it. Volume and temperature. Nope. There it is. Okay. So as I cool it down, all right, you can see that the temperature is going down. The particles are moving slower, all right? And so they're pushing against the walls of the container less hard. As I heat it up, the particles are now moving faster and faster and faster. And as it moves faster and faster, it should be expanding, but I broke the simulation. So let me just put some more particles in. So you heat it up, it expands. You cool it down, it contracts. And this is the essence of Charles' law, okay? So let me go back over here and we'll get this all wrapped up. Two others that we want to look at here is, and Dylan, if you don't mind, are you guys seeing me writing on the screen there?
Yeah.
Okay. So the next one is Avogadro's law. And this one is pretty straightforward. This is the relationship between N, which is the number of moles of my gas, and volume. And Dylan, if I can stick with you, if I think about putting a little bit of gas in the container and then putting a little bit more gas and a little bit more gas and a little bit more gas, what's going to happen to the volume of that container as we put more and more gas in it?
Get bigger.
Yep. So same sort of straight line relationship. As we put more moles of gas, that's what N is. This is the relationship between volume and moles of gas. We end up with this. And if we draw back to the combined gas law, if we just look at V and N, and we look at the P and the T going away, you end up with V over T equals a constant. Or excuse me, V over an N equals a constant. All right. And rather than bouncing back over to the simulation, I don't think we need to see that. I think all of us have blown up a balloon. You put more and more moles of gas into the balloon gets bigger. And so then the last relationship, and then I'll show you the simulation that you guys are doing, and then that'll take us to the end. The last one, I always snicker. This was a Frenchman, and his name was Gay Lussac. All right. Rude comments can be kept to yourself. Gay Lussac probably got teased mercilessly with that last name in middle school. He was the one who discovered the relationship between pressure and temperature, right? And so if you have a, let's see here, Riley, have you ever looked at like one of these spray cans? It says on the side, don't puncture, don't incinerate, don't heat. Any of these sort of spray cans, have you ever noticed a warning sign on the side of those things?
Yeah.
Okay. Well, the reason that those warnings are on there, as you heat up a gas, Riley, are the particles moving faster or slower?
They're moving faster.
And as they move faster, all right, are they banging into the wall harder or less hard?
Harder.
So what do you think that does to the pressure as temperature goes up? Pressure?
Does it also go up?
It does. Yep. And so we get the same look. So we got a lot of graphs that look the same. And so the relationship that Gay Lussac figured out was that there was this nice direct relationship between pressure and temperature of a gas. And so as the temperature goes up, the pressure goes up. And as the temperature goes down, the pressure goes down. And it looks exactly like these other relationships, except it's got the P over the T. P over T is a constant, okay? So so I wanted you to at least have seen that these four specific pieces of relationship, they're all kind of hidden in here. You see that P over T is equal to P over T, all right? So when the volume and the number of moles are ignored, the relationship shows up. The assignment that I've got for you guys, and I'll just show you what this looks like, and then give you a chance to ask any questions if you have them. And let's see here. I think Riley, tell me, are you guys seeing the physics classroom pressure concepts? A big green start button there.
Yep.
Okay. So what you'll do is there's actually 3 of these simulations, and you'll link to each of them. And once you come to the page, you're just going to click on Launch Concept Builder. And what that's going to do is it's going to take you to the actual activity that I want you to do. And so you can read the instructions here. It's basically right here in this part of the screen. That's clearly way too small to work with. So you're going to just go ahead and make it big. Riley, are you guys seeing that now full screen?
Yeah.
Okay. So you just, if we were doing Riley, we'd type in Riley. And your goal here is to answer the questions that you have. All right. You get a little trophy after you've answered the questions. And once you've done that, you're going to basically just screenshot this and you're going to upload. So you've got 3 of these to do. So you're going to have 3 screenshots. This one is related to, and actually I picked the wrong one, but it's going to look the same. So let me step out for just a second here and get to the one that I wanted to show you, not pressure concepts. Let's see, first one, pressure and temperature, right? And so pressure and temperature, that was the Gay-Lussac's law. And so you'll launch the concept builder, you'll make it big, you'll type in a name, and then you just want to make sure that you answer the questions that you see there, okay? And I just want to walk through one of them real quick. So if I begin this activity, so which of these best represents the relationship between pressure and temperature? So as the temperature goes up here, what would we expect the pressure to do? Riley, do you want to take a stab at which one of these might look like it matches up with what we were just talking about?
Is it the last one?
Yep. So you just click it, you click check answer, and you're on your way. So once you get the hang of it, it's not going to take you too long. You've got today and tomorrow to work on it. That way, if you have any questions, you can hit me up during office hours, which are going to be like basically right after this call. So 3 to 3:30 today or tomorrow. But that's basically it. And once you get all 3 of them, you'll get a trophy. Once you get all 3 sets of questions, you just take the screenshot, and that's the deal. So I'll go ahead and stop there. Any questions from you guys? Okay. Anything you want to ask, say? Otherwise, we are all set, and you guys can go and enjoy the rest of this beautiful day.